Professor Swaminathan are going to take the class. Okay. So in this first class, hope you have seen that video, IIoT, and they have talked about the transducer, and in this there is an input transducer, another is an output transducer. We have seen in one of the classes transducer, which is going to convert one form of energy into another form of energy. So here one form of energy into another form of energy, and mostly it is an one form of energy to a
Sorry to disturb, sir.
Yes, sir.
We cannot see your this thing, sir.
Oh, sorry.
Did not share, I think, sir.
No, sir. You are able to see?
Okay, sir.
Okay, sorry. Now, the input signal is maybe some of the physical signal. It is going to sense by an sensor, that is a transducer, that is called input transducer. It being processed by the processor, and after that, it need to be given to the user in form of an actuator, right? So that is called output transducer. Here, input signal is analog, and here it is electrical, mostly. Then processing in form of digital. Then again, output signal is analog. Okay. Now, again, Professor used to tell that transducers convert the signal from one physical form to another physical form. The physical form may be the thermal, electrical, mechanical, magnetic, chemical, and optical. So it is almost an energy converter. For example, microphone, which converts sound into electrical signal. Speaker, which is convert electrical into sound signal. So this is the input transducer. This is the output transducer. Antenna, which converts electromagnetic energy, electricity, and vice versa. So we have seen yesterday energy harvesting. And strain gauge, which converts strain to, though it is strain to resistance, with help of bridge circuit, it can convert into the electrical. Okay. Then definition of sensor. The characteristics of any device or material to detect the presence of particular physical quantity is called a sensor. Right? And output form of a signal, which converted to human readable form. That is important. So directly we won't get the readable form, and we have to make it process. Let's say, for example, if we have used a strain gauge, it is going to have change in capacitance, change in resistance. If you use an pressure, it is going to have change in capacitance. So all those things need to change it to electrical signal, and again it has to be processed. Then it can give it to the further readable form, right? And sensors perform some function of input by sensing or feeling the physical change characteristics of system. The response is stimuli. The stimuli may be, because if you give the stimuli, then it is going to have a physical changes, right? That is the characteristic of the system. The physical stimuli may be the temperature, light, gas, pressure, and sound, and output is the response to the stimuli. And in NPTEL, Professor thought is given the things about temperature, humidity, that is DH12, DH11, and gas sensor, which is LPG, CH4, and CO, ultrasonic sensor, and CMOS sensor, and fire detector, rain detector, PIR sensor. So there are a lot of sensors are available. So these are the few sensors, and moreover, you already know that some sensors are commercial grade, industrial grade, and middle grade. And though we have already seen as a part of this previous course, we need to see in this course also. And in this, we need to know about this static characteristics and dynamic characteristics. The static characteristics is talk about when the sensor is in steady state condition, and how the output of the sensor is changing to the input change. That is the static characteristics. Dynamic characteristics is the properties of the system or a sensor, which is how it is, if input changes, how the transient response changes, and how it is behaving with the input signal, which is varying with the time, right? and accuracy, which is represent the correctness of the output and compared to the superior system. That is the thing. Otherwise, you can say that closeness to the true value, and it is the difference between the standard and measured value. Otherwise, standard and measured value are the true value, right? Range, what is the difference between the lowest and highest value? That is the range. And why every sensor is given the range? After that, there will be the saturation going to happen. Let's say this is an input and this is an output. If it is keep on changing input, it is going to change. After some time, it is going to saturate, right? So there no sensing and no kind of response will getting from the sensor. And the resolution, that is the smallest change that the sensor can capable of sensing, right? And the resolution is important, specification towards the selection of sensors. And higher resolution is a better precision, right? So here, let's say we have so many sensors are available. Let's say, for example, for measuring the temperature, we have RTD, we have thermistor, we have thermocouple, right? And we have semiconductor temperature. In this, depends upon the application we have to choose. Already we have seen, if you want to measure the temperature of a furnace system, and if you want to measure the temperature of neonatal, so here the resolution should be plus or minus 0.1 degree. It can be plus or minus 5 degree also. So we have to. And error, the difference between the standard value and value produced by the sensor is the error, right? So what is the true value and what is the measured value? That is going to be the error. And the sensitivity indicates ratio of incremental change in the response of the system with respect to the incremental change in the input parameter, right? So what is the sensitivity? We can know that sensitivity is equal to delta of y naught divided by delta of x naught. So this is a change in input. This is change in output. Okay. So these are the things. And it can be found from the slope of the characteristics of the sensor. Let's say if you found that from the slope, you can find the sensitivity. And linearity, let's say always we ensure that our sensor should be a linear. If any, there is a deviation from that, right? So deviation of sensor value came from the particular straight line. That is that is linearity actually. And drift. So if the drift may be due to temperature, right? What is the drift? Let's say if you have an temperature sensor, this is the temperature, and this is an output. For example, voltage is given. Always you will find that it should be the graph, but sometime it may drift by this value also, right? It may be due to the aging, or it may be due to the temperature, or it may be due to this characteristics of the sensor for using a long time. And we know that repeatability, what is the deviation between the measurement in sequence under the same condition? So let's say what is the deviation is going to get, you get the same condition. What are the same condition? If you have a flow sensor, you are giving the water flow, for example, through using 1 HP motor at 25 degrees Celsius, and it is by using same observer, right? So all those things are same. These are the same conditions. That is a repeatability. There are so many static characteristics are there. We have seen in our previous thing, but in this NPTEL lecture, professor only told about these characteristics. Dynamic characteristics. So dynamic characteristics already will change. How it is going to respond if there is a change in input? Because everything will have a change in input for sensor, but the change in input varies with the time. For example, vibration, right? And sound signal, ultrasound, RF signal. So all those things are which is going to have a change in the input. For example, if you have a zero order system, in zero order system, you have a wall, right? Let's say you have a wall, and it is attached to a potentiometer or this kind of an rotary displacement, right? So it is only a resistor. In resistor, there is no storage of memory. So what is going to happen? You're going to get input signal without any delay, right? So the response of this sensor, if rotary sensor is an potentiometer or resistive type, we are going to get the signal without any delay. And it does not include the energy storing elements, right? And for example, potentiometer measure linear and rotary displacement. And always, maybe for mechanical and civil participants here, always you think that why we have studied B2B, basic electrical and electronics, because most of the system to analyze, electrical engineer, they'll make only into RLC, right? They make RLC in different combination, parallel, series, all those combination. For analyzing, they'll make it as an RLC, whether it is a motor or transformer or a transistor, right? With help of a transistor, will have again a current source, all those things, right? So we'll make everything in a voltage source, current source, and RCL, right? We'll make everything for analyzing purpose. That is the need for the studying, whether it is a skin or any sensor, right? So all those things can be modeled into a electrical circuit. And if it is an first order system, so there will be change in the output as input changes, but it's going to reach the final value gradually, right? It's going to reach the final value gradually. And it is consist of an energy storage and dissipation element, and it is a second order system. Is a complex output response, and here it is depends upon the element. Sometimes if you, let's say this is the input and this is the output, the first order system goes like this. Second order system depends upon whether it is a critically damped, under damped or over damped. It will go, let's say this is a true value, it will go like this, it maybe oscillates also. So accordingly, you have to adjust some of the parameter of the sensor. Now, in sensor classification, we have passive and active, analog and digital, scalar and vector. Okay. So in passive sensor, it is can't independently sense the input. Okay. For example, if you have accelerometer, you need to give the power. Soil sensor, again you need to give the power. Water level, you need to give the power. So it requires the power, or it needs some separate excitation circuit to sense the change in the physical phenomena, right? And the active sensor, it is sense the independently sense without any power. For example, radar, right? And sounder, laser altimeter sensors, thermocouple. So all those things are does not need a power supply. So there is an active sensor. And we have an analog sensor. In this, yes, this is active sensor. So it does not require any power supply. Now, again we have analog sensor. This output is a continuous function of his input parameter. So again, if it is a temperature sensor RTD and it is a temperature, then change in distance will be continuous function of the time according to the temperature. LDR also change in resistance. Analog pressure sensor also, this if the strain gauge has change in resistance. Analog Hall effect is change in the voltage. right? So it is the analog sensor. The digital sensor, it is having the binary nature, and these are the designs to overcome the analog sensor, because what is the disadvantage of analog sensor? We can't transmit for the longer distance, and with the digital sensor it can be done, and it is more not it is more immune to the noise, electromagnetic interference, right? So what is the digital? They have analog sensor, add additional electronics to make a digital signal, right? That is an digital signal. For example, passive infrared sensors, that is a digital temperature sensor, that is again DS1620, that is a digital sensor. Scalar sensor. If a sensor measures only its magnitude, that is a scalar sensor, and it is not measured by its the direction of the input parameter, right? So it is not going to give which direction it comes. Let's say if we place a temperature sensor, it does not give the heat is coming from here or heat is coming from here or heat is coming from here, right? That is only the scalar sensor. Like for example, gas, train, color, smoke sensor, all those things are scalar. But few sensor will require the vector sensor. It is going to give magnitude of the direction and as well as the orientation of the input parameter. For example, accelerometer, we have 3-axis accelerometer and gyroscope and magnetic field and motion detectors, right? So all those things, right? All those things are a direction. It is going to give the direction of the input parameter, orientation of the input parameter. Here we have energy. Okay. So now, until now, we have seen about the sensors. Now we are going to see about the actuator. Here, for actuator, for example, if you take a motor is the actuator, relay is an actuator, right? Speaker is an actuator. So first we need to give the energy to the actuator, right? And it is going to give motion as force. Motion as force to the force. So, and why the signal? Like for example, if you have a motor, if you give constant power or constant voltage, so you can't control the speed or some other characteristics of the motor. But it is additionally, if along with that, if you give the signal, if any driver is there, then we can control the speed of the motor, right? So it is deal with the control action required the mechanical action. Mechanical or these are the electromechanical devices also involved in this. For example, the professor took an relay as one of the actuator. Hope you know. So this is the common. It is normally closed and this is normally open, and we can give the ground and VCC, right, for operating the relay, and we can give the signal here, right? We can give the signal to switch on or switch off. We can give the signal here. Okay. So like this, we can operate 4 relays separately. And here, a control signal is the input to the actuator, and the energy source is necessary for the operation, right? That is a thing. Let's see if you want to change the if you have a linear actuator, you want to change the direction, the control signal should be according like that. If you have a motor, the control signal should be according such that it has to change it the speed variation, right? And everything the actuator will have it is in micro and as well as the macro scales, right? So if you take it as a MEMS, then it will be in micro, and it can be in the macro scales like motors. And for example, this electric motor, solenoid, hard drive, stepper motor, COM drive, hydraulic cylinder, piezoelectric actuator, pneumatic actuator, all few of this actuators. And in classification of actuators, we have electric linear and electric rotary and fluid power linear, fluid power rotary, linear chain actuator, manual linear, manual rotary. We're going to see one by one. So the linear actuator, mostly you can say it as a solenoid valve. Right? This is a solenoid valve. For example, the mechanical device which containing the linear gates, motors, and driving mechanisms, all those things are linear actuators, and which is going to convert electrical energy into the linear displacement. This application, we can say that, including electrical bell, opening and closing of dampers, locking doors, and braking machine motions, all those things are coming to the electrical linear actuator. And electrical rotary, by giving the electrical energy, it is going to give the rotational motion, and including, for example, best example is motor, and practical examples are given as a quarter 10 volts, windows, and robotics. All those things are a few examples on the electrical rotary actuator. Another is the fluid power linear actuator. So here, instead of electrical, we are going to give the fluid. The fluid may be the hydraulic fluid, gas, or differential air pressure. From there, we can going to move the piston by using piston mechanism and cylinder. We're going to move the mechanical devices, all mechanical devices. So it is going to produce a linear displacement. And where it can be used, mostly it can be used in the clamping and welding applications. Fluid power rotary actuator. By using fluid power, there will be rotary. Again, the fluid may be fluid, gas, or differential air pressure. So it is consist of a cylinder depression as well as the gearing mechanism to rotate it, right? Which is going to convert the hydraulic fluid, gas, or differential air pressure into the rotational motion. And mostly it is used in the opening and closing of dampers, doors, and clamping to be used. Another is a linear chain actuator. So here, this mechanical device consists of the sprocket and sections of chain. So here it is rotates. Accordingly, it goes ups and down. So it is going to produce a linear motion by the free and especially design chains. And it is mostly used in the motion control applications. And this is a manual displacement linear actuator. So this is translation of the manual rotator screw circuits. So it is consists of gearboxes, hand operated knobs or wheels. So it is an manually operated. And manually rotary actuator, again by using the manually manually rotated screws, levers, gears, all those things are few examples, and it can be used for examples are hand operated knobs, levers, hand wheels, and gearboxes are the few examples, and mostly it is used in the operation of the valves. Now, so with this with this, they have concluded the actuator and the sensor, right? Do you have any doubt up to this? Do you have any doubt up to this?
No, sir, no.
Okay. Now, we slightly go into the communication protocol. Why communication protocol is necessary? Let's say you have a sensor. You have a sensor. You have a sensor. Then you have a processor. Right? Then you have a radio. Transmitter, communication. Then you have a cloud. Then you have a gateway. Right? And gateway to application. Right? Now, how the sensor, after processing, after transmission, it has to communicate to the gateway. How it is possible? So there are so many protocols are there, right? It is not only from process to gateway. Sometimes within the IoT node 1, IoT node 2, within that also we need to communicate. Within this also we need to communicate. How we are going to communicate to each other, right? So what protocol can be used? So if you select any protocol, basic thing is power consumption, then data rate, how many devices are connected. So whether one to one, one to many, how it is connected, and what form of network is going to form. So all those things are need to take care of. The example here they taken IEEE 802.15.4 Zigbee 6 low power PAN and a wireless HART, Z-Wave, ISA 100, Bluetooth, NFC, RFID. These are the three communication protocol used in the important protocol used for the IoT, right? Now, for mechanical, civil, and chemical participants, because now we are going to talk about different layers, right? Different layers. So, what is the layer? So, let's say if you take it, every communication system, right? That is have a OSI layer. So OSI means open system interconnection. So open system interconnection. Interconnections. So what is this open source interconnection? Right? So this is a conceptual model created by a ISO. Right? Prasant sir, kindly unmute yourself. Prasant sir, unmute yourself. Prasant sir. Hello. Prasant sir, kindly unmute yourself. So this is a conceptual model created by international organization, that is for sciences, that is ISO. So why it is required? So it enables the diverse communication at the standard protocol.
Sir, you can mute him.
No, sir, since it is open, I can't unmute it. Unmute it. Prasad sir, kindly mute yourself. Anybody having last number? So you can call him.
Hey, Swami.
Now, let's say this is having 7 layers. So physical layer, then data link layer, then we have a network layer, transport layer, session layer, presentation layer, and application layer. Now, in form of a mechanical terms, we are going to see how it is related, right? For example, what is a physical layer? So physical layer is a hardware. Hardware. For example, wires and signal. Let's say in mechanical analogy, what is physical layer? Roads, trucks, fuel, that is which is going to carry physical component. That is a physical layer. Then in actual manner, cables, RF signals, voltages. So how the signal is going, right? So that is maybe fiber optic Wi-Fi signal. That is a physical layer. Next one is data link layer. Let's say if data is used to flow, then what data link layer has to do? Let's say like in mechanical analogy, we have a traffic rules, number plates, and signals, right? So many things will be there. Same thing in data link layer, to ensure that data frames won't collide, and it is add MAC address where to reach, right? Where it is generated, like vehicle number, right? That is a data link layer. And after that, GPS, that is a network layer, map and GPS. So, which is the best path to deliver the data, right? That is required. For example, mechanical analogy, if we have used a GPS with internet connection, we used to tell that best path to deliver to reach the particular destination. Same thing here, IP addresses, and it is going to have a best path to deliver the data. Here, IP address, routers, all those things are network layer. Another is a transport layer. Here, how, let's say if you're sending your package is transported. Now, sometimes you'll get OTP, sometimes you won't get OTP, sometimes you need to acknowledge your sender. So all those things are there. So how this package is delivered? Intact, in order, without loss, right? And moreover, if you have a big package, let's say item, this, let's say if you are going to shift the houses, you want to shift the house to one place to another, they won't shift all the things, the key won't keep on a single box. They'll segregate into the small box, small packets, and error free, and ordered delivery, that is a TCP. Let's say sending some data without any guarantee, that is a UDP. So these are the protocols. So TCP and UDP are protocols. I like to hear from circuit branches, what is TCP? Circuit branch participants, what is a TCP?
Transfer control protocol, sir. Transfer control protocol.
Transmission control protocol.
Transmission control.
What is UDP?
User datagram
protocol.
UDP is user datagram protocol. So this is the some of the things. Let's say wherever you are required, some of the things you require TCP, and sometimes you require the UDP. It depends upon the application. Let's say if you found that some losses are, or you can bear some losses of packets, so you can go for the UDP, right? So that can be only speed is matter. Only the speed is matter, but the data loss can be done. Let's say if you're watching a movie, they used to do with UDP, right? Some data loss does not create much defects in your movie. But
excuse me, sir. Sir, can we consider TCP for global transactions and UDP for local transactions?
sir, you can't consider
Means
global,
our-
sir.
For example, can I say something like if we want to transfer data between two mobiles which are very nearer,
Okay, sir.
so can I consider it is a UDP?
It is not like that, sir. Let's say if you're watching a movie,
Sir.
so it is data is being transmitted, but there, if any data loss is happening inside, only some pixel is going to vary. You can't able to recognize that one. And moreover, it does not require always as I receive the data, and it does not have the header files. But though you are sending the data mobile here to here, you are going to send one Excel file. But the data loss cannot be, we can't tolerate the data loss, right? No, I can send some Excel file. The particular rows are not received. So that is not the correct one. So where we can tolerate occasional packet loss is tolerable, and you need only the speed and efficiency is the matter, then you can go for UDP.
Okay, sir.
Another is a session layer. So here, session layer is, let's say if two persons are communicating, they have to understand, let's say I'm taking the class, I have to understand whether you are there or not, right? So I have to understand, yes, at least by seeing that your Gmeet photographs, I can understand, yes, you are available, so that I'm talking to you, right? So that each thing has to be understand that, yes, we are in touch with each other, so that we can have the communication sessions, right? And both the things will know when to stop, when to start. That is a session layer. Another is a presentation layer. Here, if you send a CAD file in a format, and the receiver computer going to convert there into the software format, right? So that is a presentation layer. So we can send anything like a CAD file. It may be with any software. So it can be the computer going to convert into the user format in the software file, right? So it is going to translate the data, for example, encryption, compression, all those things, and where the application can understand it. We're going to see. For example, this is a JPEG, MP4, and encryption, all the for the example. Last layer is the application. So for application, we can see Gmail is an application, WhatsApp is an application, Zoom is an application, Gmail is an application, where it is used. So where the application finally So these are the different layers. So whether all the protocols is whether it is having all 7 layers, we can't say. It's not necessary to have all the 7 layers individually. Some of the layers are merged to single layer, right? So it is depends upon the protocol. We have a layers. Let's say some layers will have only, some protocol will have only 3 layers, some will have 4, right? So it is depends upon the protocol. Sir, please mute yourself. Please mute yourself. Thank you. Now we are talking about the frequency. Now, while seeing the protocol, we will talk about the some of these layers, and we'll talk about the frequency. So whether we can operate in all frequency, that is not possible, right? So like for example, we can operate in the unlicensed wireless devices, right? For example, Wi-Fi, Bluetooth, RFID, we can use it, right? So we can't use the licensed frequency range, but we can use unlicensed frequency range. So that's why we call it ISM frequency. That is ISM bands. What ISM represent? Industrial, scientific, and medical application, right? Like for TV and cellular, the bands are there. We can't use in particular band, but we can use it in this band. So 2.4 gigahertz is coming in the ISM band, and each country will have their own things, right? So 2.5 is universally is okay, but if you go in 753 megahertz, so accordingly we have to check the country. Accordingly, we need to check their ISM bands available in their country. That is important. Now we are starting with IEEE 802.15.4. Here it is a framework meant for lower layers, MAC and physical layer, and it is for wireless personal area network, right? WPAN. And the physical layer depends upon frequency band, transmission power, modulation scheme of the link, right? This physical layer will defines these are the things: frequency band, transmission power, and modulation scheme. So you know what is a frequency band and transmission, right? In transmission power, so how many dBm, 2 dBm, all those things, transmission and modulation scheme. So here, hope you know AM, FM, right? All those modulation scheme in radio, but in digital, we'll have different modulation schemes are there. So what modulation schemes being used, right? And here, this MAC is going to define as a medium access and flow control frames. How this you're going to access the medium and how the flow control of the frames can be done. So this kind of a protocol mostly used for low power, low cost manufacturing operation and low speed communication between the neighboring device within the 75 meter. And this is utilizes this direct sequence spectrum. It is no need to go into the communication, and it is also using phase shift keying modulation to encode the information. And here BPSK, they use binary phase shift keying. It is 868 or uh, 868 or 915 megahertz. So it is a binary phase shift keying. If we use this kind of a modulation, we can transmit the data rate 20 or 40 kbps, depends upon the frequency. Another is offset quadrature. Offset quadrature phase shift keying. It is 2.5 Hz, data rate is around 250 kbps. So this direct sequence spectrum, which is standard because it is tolerant to the noise and the interference, that's by improving the link reliability. Let's say if you have two devices communicating each other, we have to check that the link reliability should be more so that it can communicate each other continuously, right? Otherwise, without loss, we have to communicate, right? So in this, I request the mechanical, civil, chemical participants, no need to worry very deep. So here we can say MAC and physical layer. The physical layer already we have considered, it is a physical level. The physical level, what is the device will do, what is the frequency band is going to operate, what is the transmission power, or what is the modulation scheme. And the MAC, it is a medium access and flow control, right? The application is given low power, low cost. And they are using the DSS, the direct sequence spectrum, and it is used as the phase shift keying for modulating information. In phase shift keying, they are using two types, only BPSK, another is an offset quadrature with different frequency. It is also catering the different data rate. And why it is being used DSSK? It is a tolerant to noise and interference, right? And here the features are preferable nature of transmission line is line of sight, and the standard range of transmission is 10 to 75 meter, and the transmission of data uses CSMA CA, the carrier sends multiple access the collision avoidance scheme, so where avoidance will be less. So what is avoidance? If 2 or 3 devices talks to each other, how it is avoidance can be taken place. That is the thing. And here, how it is an transmission is taken place, short packets. So very less time only is taken for transmit the data packets. So that is reducing the consumption of power. And here star network topology or peer-to-peer network topology is included. So what is the star network topology? You have a hub,
No idea, sir.
you have a device, you have a device here, 1, 2. So this is the star, right? So it can be used for the star and peer-to-peer. Peer-to-peer is 1 to 1, right? 1 to 1. That is possible with this, right? So if you require if you require all those things and you want to use the star and peer-to-peer, you can use this. And there are so many variations are in this. For example, 2003. This is the basic version is operated in these are the frequency. And 2006, it is known as the B. This provides the data rate, and it is going to go OQPSK operate in the range, and it can have a very high data rate. Right? Another thing is A. They increase the range capability. So here, ultra sequence wild range. This is the range, and you can see this is the low band, this is the high band, and CSS approach ISM band is 2.4 GHz. These are the range capability. Another is one of the version is C, is provide the 70 MHz band in China, either by OQPSK or NQPSK, transmission rate of 250 kbps. Another is an 950 MHz band in Japan, whether it is a Gaussian phase frequency modulation scheme, it is going to achieve the 100 kbps at the BBSK with the data rate of 20 kbps. Another is E, defines the MAC development towards the ISA SP application for industry application. And F defines the physical layer 43 MHz band for RFID application, and 2.4 GHz frequency band and UWB. Other thing is G, and it can be used for the smart grid applications and majorly for energy industry. So if you see it, this is the basic thing. From that, one is some of the things improved depends upon the country and depends upon the application also, right? And we are going to ZigBee. Here, ZigBee is framework for the medium range communication IoT connectivity, and it defines the physical or medium access control layers, and it is enabling the interoperability between the multiple devices, low data rates. So we are going to see how it is going to use it in multiple devices, and is going to operate in 3 frequency. One is 868 MHz, one channel using transmission up to 20 kbps. 902 928 MHz, 10 channels using data transmission rate to 40 kbps. 2.4 GHz, 16 channels using data transmission rate up to 250 kbps. Right? So these are the speed and these are the frequency ranges. And what are the features of ZigBee? Use BPSK, and for 2.4 GHz using OQPSK, and here data transfer takes place 128 bits per packet size, and maximum allowed payload is 104, and nature of transmission is line of sight. So line of sight is if you have a transmitter and should be the receiver, there should not be any obstacle, right? So that is the line of sight, and the standard range of transmission is 70 meters. Here, one of the features are relaying packets auto transmission over greater distance that is possible, and it is going to produce a low power consumption around 1 milliwatt per ZigBee module, that is going to be low power, and it is having adaptable duty cycle. It is having low data rates, 20 to 50 kilobytes, and coverage area also 10 to 100 meter, depends upon strength of power. and it can make star, peer-to-peer and cluster tree and mesh being popular. So what is this one? So we can going to see star. For example, let's say you have consider this E as an IoT node, right? IoT node. What is IoT node? For example, if you take a home automation, right? If you take a home automation, IoT nodes may be the geyser, refrigerator, right? Other thing is some kind of an microwave oven, okay, window. So all those things are connected to a coordinator, single device. From this, it can connect it to the gateway, right? Otherwise, coordinator may be also the gateway. But same thing, if you want to use in forest fire reduction, right? So you can't keep the coordinator and you can't keep the IoT node. What we have to do, one of the thing is you can keep the router and you have the end device. So end devices are IoT nodes are transmitting due to the router, and router within themselves going to communicate and how somehow it is going to transmit to the coordinator. So end device duty is just to tell yes, fire is related or not. The router is going to get the value by nearby the IoT node, that is end device. It is somehow it is transmitting the coordinator. This is the mesh. Another is a cluster. So we have a end device here. This is we have a router, and it is going to, without communication between the router, it is directly communicating. All the routers are communicating with the coordinator. Okay, so that is the different topologies. So previously you have seen in previous protocol only two things, only peer-to-peer and star. In this we can make star and we can make mesh, right? And we can make clusters tree also with this ZigBee protocol. So here already we have seen three types of nodes: coordinators, routers, and end devices, right? So this is not going to contribute in the routing, and routers are connected to the coordinator. Other routers have 0 or more children nodes, contribute in multi-hopping routing. So coordinators initializing, maintaining the controlling the network. There is one and only one per network is a coordinator. And the star topology, no router is required, one coordinator or 0 or more end devices. In mesh and tree topology, one coordinator maintains the several routers and end devices. So again, each cluster in the cluster tree network involves a coordinator through the several leaf nodes, and the coordinators are linked to the parent coordinator that initiate the entire network. Here, ZigBee standard comes in the two variant, ZigBee and the ZigBee Pro. The ZigBee Pro offers the scalability, security, and improved performance replacing many-to-one routing scheme. And this is 6 low power wireless personal area networks. So this 6 came from the IPv6 packet transmission in low power noisy networks such as an IEEE 802.15.14. This is also going to operate in the 2 frequencies. So worldwide they're using 2400 to 2483.5. In North America they're using 902 to 929 megahertz, and it is used as unslotted CSMA and CA mode. And the features are this data format are to fit with this IEEE 802.4 for lower stream, and the maximum transmission is the bytes in the length, and here IEEE 802 is only 127. Then what is going to do? Because it is having this much bytes, and it is having only this much bytes, and the application layer is introduced between the MAC and network layer that provides the packet fragmentation and compression of header and routing. So all those things are introduced to make this 180 to 127 bits. And the fragmentation to fit the intact IPv4 packet into distinct IEEE disk frame, that is approximately 106 bytes, and the fragmentation getter allows 2048 bytes packet size in fragmentation, and using fragmentation and reassembly, and these 128 byte IPv6 frames are transmitted over this IEEE radio channel to several smaller segments. So here, if you can see, the radio, everything is in this one, but how these packets are arranged, that is different. And here every fragment includes the header. Here features are the header compression to reduce the transmission overhead and allows the efficient transmission of payload. And IPv6 addresses are compressed in 6 low power band, and it is a 8-bit UDP header is there, and 40-bit IPv6 header is there. And here also it is a stateless auto configuration, allow any device to create IPv6 address automatically divide the external field with. So what is the stateless and the stateful? Circuit branch students, please. Circuit branch students. Circuit branch students, what is stateless and stateful in circuit branch students? What is the stateless and stateful? The stateless is each request is treated as an independent. It won't remember the previous request. But stateful is the information of the past interaction also are going to influence the future one, right? So that is the stateless and stateful. And here the features of 6 low power wireless network is mesh sender utilizes link layer to forward data packets, and route over utilizes the network layer as an IP address. And for security, they are using AES 128 bits encryption, right? So this is the two things. It's the mesh sender, route over, right? So two schemes the professor used, right? So this is called an application layer. Everything is in transmission layer, network layer. This is a low power thing, MAC layer, physical layer. In this, they call as an adaptation layer, right? It is going to adapt adaptation layer, route over. Okay. Okay. We'll tomorrow next class we'll see this. Do you have any doubt?
No, sir.
Okay.
No, sir.
Okay. Tomorrow you can attend the classes, right? Tomorrow you can attend the class of machine learning thing, NPTEL lecture, NPTEL
Data science.
the data science, sir.
Yes.
Right? Okay.
Problem solving, sir. Problem solving session.
Sorry, you can attend tomorrow.
Okay, sir.
Thank you.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.